Today we are going to solve a couple of questions on matrices. So let's take a look at the first question. The first question is, we need to solve a system of linear equations using Cramer's rule. The system of linear equations are 5x minus 7y plus z equals to 11, 6x minus 8y minus z equals to 15, and 3x plus 2y minus 6z equals to 7. So these are given to us. Now we need to find whatever is necessary. Therefore, delta equals to determinant 5 minus 7, 1, 6 minus 8 minus 1, and 3, 2 minus 6. Solving this, we get 5 into 48 plus 2 plus 7 into minus 36 plus 3 plus 1 into 12 plus 24. This gives us 55, which is not equals to 0. Now we need to find delta 1, which is 11 minus 7, 1, 6, 15 minus 1, and 3, 7 minus 6. Solving this, we get 11 into 48 plus 2 plus 7 into minus 90 plus 7 plus 1 into 30 plus 56, which also gives us 55. Now for delta 2, we have 5, 11, 1, 6, 15 minus 1, and 3, 7 minus 6. This gives us 5 into minus 90 plus 7 minus 11 into minus 36 plus 3 plus 1 into 42 minus 45. This gives us minus 55. Also for delta 3, we have 5 minus 7, 11, 6 minus 8, 15, and 3, 2, 7. Solving this, we get minus 55. Then, by Cramer's rule, x equals to delta 1 by delta, which gives us 55 by 51 equals to 1. For y, we have delta 2 by delta, which gives us minus 55 by 55 equals to minus 1. And z equals to delta 3 by delta, which also gives us minus 55 by 55 equals to minus 1. Thus, these are the solutions: x equals to 1, y equals to minus 1, and z equals to minus 1 for the given system of linear equations. Now for the second equation, we have question number 2. We need to verify Cayley-Hamilton's theorem for a given matrix. The matrix is A equals to 2, minus 1, 1, minus 1, 2, minus 1, then 1, minus 1, 2. This is the given matrix. So first, we will find out the characteristic equation. The characteristic equation of A is mod A minus lambda I. This implies determinant 2 minus lambda minus 1 1 minus 1 2 minus lambda minus 1 and 1 minus 1 2 minus lambda equals to 0. This is the determinant. Now we need to operate this. So operating the first row with R1 plus R2, we get 1 minus lambda 0, minus 1 2 minus lambda minus 1 and 1 minus 1 2 minus lambda equals to 0. Now operating column wise. First we did it row wise, now we are doing it column wise. The second column C2 minus C1. So from this we get 1 minus lambda 0 0, minus 1 3 minus lambda minus 1 and 1 minus 2 2 minus lambda equals to 0. So expanding through first row, we get 1 minus lambda into 3 minus lambda into 2 minus lambda minus 2 equals to 0. This implies minus lambda cube plus 6 lambda square minus 9 lambda plus 4 equals to 0, which implies lambda cube minus 6 lambda square plus 9 lambda minus 4 equals to 0. So this is the characteristic equation. Now for Cayley-Hamilton theorem, the matrix A must satisfy this equation, which is equation number 1. So we are going to put lambda equals to A. Then we get A cube minus 6A square plus 9A minus 4I, which is the unit matrix. Now we are going to find A square. We need to find A cube. For that, first we will find A square. So A square equals to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Multiplying this with the same thing, 2 minus 1 1 minus 1 2 minus 1 and 1 minus 1 2. So solving this, we get 6 minus 5 5 minus 5 6 minus 5 and 5 minus 5 6. After finding A square, we need to find A cube. So A cube equals to A square into A. We found A square to be 6 minus 5 5 minus 5 6 minus 5 and 5 minus 5 6. Multiplying this with A, which was 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Again solving this, we are going to get 22 minus 21 21 minus 21 22 minus 21 and 21 minus 21 22. So on putting the values of A square and A cube and the unit matrix I in RHS, we get this was A cube minus 6A square plus 9A minus 4I. So we're going to put the values. This was A cube, then 6A square, the value of A square was 6 minus 5 5 minus 5 6 minus 5 and 5 minus 5 6. Then plus 9 the value of A, then the value of the unit matrix, which is 1 0 0 0 1 0 0 0 1. After solving all this, we are going to get 0 0 0 0 0 0 0 0 0, which is equals to 0. Hence, the Cayley-Hamilton theorem is verified. Now we have to find A inverse. For A inverse, we need to multiply A inverse on the both sides of equation number 1. So we are going to get A cube A inverse minus 6A square A inverse plus 9A A inverse minus 4I A inverse equals to 0. This gives us A square minus 6A plus 9I minus 4A inverse equals to 0. So 4A inverse equals to A square minus 6A plus 9I. So we are going to put the values again. This is the value of A square minus 6 the value of A plus 9 the value of unit matrix. Solving this, we get 4A inverse equals to 3 1 minus 1 1 3 1 and 1 minus 1 1 3. Hence, A inverse equals to 1 by 4 3 1 minus 1 1 3 1 minus 1 1 3. This is the value of A inverse. Our third question is a very simple one. Question number 3. We are given A to be a square matrix of order 3 having eigenvalues 1, minus 1 and 0. Then we need to find the determinant of I plus A to the power 100. So, since the eigenvalue of matrix A, the eigenvalues are 1, minus 1 and 0. Therefore, the eigenvalues of the matrix A to the power 100 would be 1 to the power 100, minus 1 to the power 100 and 0 to the power 100, which is 1, 1 and 0. Now the eigenvalues of the matrix I plus A to the power 100 would be 1 plus 1, 1 plus 1 and 1 plus 0, which are 2, 2 and 1. Thus, the determinant I plus A power 100 equals to 2 into 2 into 1, which is equals to 4. So in this way we find the determinant of I plus A to the power 100.